Mm. Namaste, everybody. Hi, Jacob.
Namaste. Hi.
Thank you. All right, let's start the music. You guys like to drop in, just clear your space, clear your energy in your body. Turn your attention to the tunnel side of your soul. We want to clear our space, clear the body, bring attention to any of the resistance, disturbances within the field, and intuitively clear it. This helps to awaken intelligence and love, helps you to think clearly, get into a more conscious state of mind. And just meditate like this for a couple minutes. When you're ready, you come out of the meditation. So an enlightened principle is that there's a big difference between perceiving and remembering, or knowledge and information. In mathematics, we're generally taught. Hi, Carlos, by the way. Namaste. Nice. Thanks for being here. In mathematics, we're generally taught to learn to do mathematics, learn to go through a sequence of steps, um, learn to memorize mathematics. And we're taught this from a very young age. So one of the first things we learn is our times tables. Why is it a table? Well, originally you'd see it in a table format and you would memorize each of the times tables. So memorize 11 times 11, right? So we were trained to do this since we were very little. Uh, if I were to ask you what's 17 times 17 in base 16, you probably have no idea because you never memorized the base 16 times table, right? But Jacob, what is it? Okay. You'll know by the end of the day. So 17 times 17 in base 16, or 15 times 16 in base 16, or 15 times 15 in base 16. You could do those if you learned to see them. Now, if you learn to see your times tables, you're developing a completely different paradigm around mathematics. Perhaps you'll learn to see the Gaussian curvature more clearly, which is an advanced topic, which you can calculate using derivatives and dot products and things, or various topics, right, in mathematics. So there was a point when I realized I didn't know how to multiply. And this was in relatively recently, 5, 6 years ago. I thought to myself, wow, if I can't see these things as self-evident, I don't feel that I actually know how to do it. If I can't see the instantaneous insight that 11 times 11 is 121, if I can't see that, I don't feel that I know it at the level of enlightenment, and I don't feel it's very relevant to me. It's relevant as a utility, but not as a personal augmentation of my mind. So, can you guys hear me fine, by the way? Do I sound good? Okay, cool. Do I sound crisp with this new mic? Good. Thanks for letting me know. I like my new mic. So, so if we can learn to perceive perfect squares, 11 times 11, 12 times 12, 21 times 21, 31 times 31. I mean, this maybe give you guys just a moment. Do you have any idea what 31 times 31 is? Just maybe take a moment. I won't ask anybody, just for yourself. Can you have any sense of what that is? And perhaps you're saying, okay, well, it's more than 900, which is 30 times 30, but then maybe you're using a trick there too, right? Why is 900 30 times 30? Let's make sure you can see that. So mathematics is a purely abstract concept. Nice. Yeah, Richard Feynman was along these lines of thought. And he once said that he doesn't just do math, he knows math. He said something like that. And it makes a big difference because we want to really know math. We don't want to just be able to do it, especially in the age of AI. I think if you can just do it, maybe you might as well outsource it to the AI. But if you get to see it for yourself, the AI can't see it for you, right? It's like going to the gym. Or going for a run. You want to go for a run? The AI can't do that for you. You can hire a machine to run, but that's not you running. So yeah, Richard Feynman is great about that. Um, so let's take a look at what I mean by this. Did my screen just pop up? Did you guys see it switch, or did it just go at the end?
Yeah, we can see.
It switched.
Okay. So let's take a look. So here's one way to visualize 11 times. Okay, so this will be 10 times 10 as an area. 11 times 11. 12 times 12. Why is it 12 times 12? Because it's 12 wide and 12 tall. This is 13 wide and 13 tall. The light blue area is 10 by 10. So that's 100. The oranges are all 10 wide, 10 by something else, right? So I have this going a little fast. Let's try, so this is try 11 times 11. Oops. So 11 times 11. So we have the main area is 100. It's 10 times 10. Then we have 10 on top, 10 on the side, and 1 in the corner. So 11 times 11 is 1 10 10, 2 10s, and 1. Is this new for anybody? Does it seem too obvious, too easy, or is it? Let's hear from you, Jacob.
Oh, I'm still trying to understand what's going on.
Okay. So sometimes I'm not sure if I'm being too obvious or doing the opposite. So so let's do it together. Just me and Jacob. Jacob, keep your mic on. Um, let's walk through this together, and then everybody else can follow along our journey of this. So if this is 10 tall here, and this is 10 wide, how many do we have in this main section here?
So we have a 10 by 10, 100.
100, which is by definition 10 tenths. That's the definition of 100. So we haven't memorized anything there. We might even say it's 1 10 10, 1 10 by 10. Okay. And then how many do we have here?
So that'll be 9.
Is it? Because this
Oh.
was, right?
Sorry. Yeah,
Like,
that's
no,
10.
is it 10? Okay.
That's
So
10.
take a moment, and this is the thing. We have to kind of become aware of all the components here.
Okay.
So if that's 10, and then this is also
That's
10.
also 10.
Now, why are they 10? Because they were as wide as the light blue area, right? Okay. And then we get this extra part here,
Yeah.
which is 1. So we can now see in an instantaneous insight, 11 times 11 is 121.
Okay.
So
This one makes sense with how I break up the math in my head. But seeing it geometrically like this, that's okay. I like that.
yeah, because it'll empower you. So watch this. So let's see, perhaps let's do 12 times 12 and just see if you can see that 12 times 12 is 100 for the light blue. We have now, how many on top do we have, Jacob?
Okay, so 20 now.
Okay, and how many do we have?
Okay, 20 and then plus 4, and then 144. Okay.
And you can see it.
Okay.
So imagine this was your flashcard when you were 8, 9, 10, whenever you might have learned times 12. You would actually be seeing, okay, it's actually it's areas, or it's a geometry. Now, mathematics is not a geometry, right? So these numbers are purely abstract. We're simply representing them as area, which can be useful. A way to see it, literally. So what do you think would be the case if we did 13 times 13?
It'll be very similar. You would have 30 on top, 30 on the side, then you have a 3 by 3 in the top right corner.
Nice. Then we have 169. Cool. Carlos, how's this looking for you? Cool. You wanna talk?
Yeah, this is kind of mind blowing because it does make sense, but I'm also like trying to take it in because yeah,
Nice. Yeah, I mean,
this is cool.
well, the whole idea is like we're gonna awaken genius. You know, I said that on a few of my reels, awaken genius. Well, I think you can awaken genius. I know you can by beginning to perceive these for yourself. So usually in mathematics, there's an intermediary, like some sort of imaginary authority, and that's really just in our own minds. But now you can see 13 times 13. There's no special you know, you don't have to carry the one and do all that stuff that maybe you don't know why it even works. Why do we even do that? You don't have to memorize it. This is a conversation between you and the universe. That's what we've made it, a conversation with the universe. All right, so I don't want to go too fast though, because we can take this to three-dimensional levels. We can do all kinds of fun things with this very quickly. Let's just take our time. 14 times 14. I'll give you guys 10 seconds to think if you can see it in your mind before I push play. So Jacob, how many do we have on the top and the side?
I love 40 on top, 40 on the side, and then in that little corner left, 4 by 4, 16. Yeah.
Beautiful. By the way, if you guys want to grab a piece of paper and do this by hand, that's totally fine too. You don't have to draw every square, right? You can make it just 4 sections if you want. And over time, you'll be able to just close your eyes and see it. And the more you've had the experiences with paper or with visualization like this, the more you'll be able to just close your eyes and see it. So, okay, so we can see here, we've got 100, 2 16s, 2 40s, and 16. So
You can if I can add, you can think of it as um like a plus b, within the parentheses, squaring it, and then you get your a squared plus 2ab plus b squared. The orange is the 2ab.
You're a little ahead of the class.
Sorry.
So eventually we'll generalize this and see that we can do algebra this way. And in fact, you can do calculus this way too. So this is not just arithmetic, it goes further and further. So so in mathematics, x plus y squared equals x squared plus 2xy plus y squared. And it's actually referencing each of these 4 parts. And those are called quadratic functions. Why are they called quadratic functions? They only have 3 parts. Well, they come from 4 sections like this. Quadratic functions.
Thank you.
Isn't that interesting? That it comes from 4 sections. That's why it's called quadratics. All right.
There's so much that you miss out in public schooling.
What'd you say?
There is so much that you miss out in public schooling.
Yeah. Well, we're seeking to change that. That's what the mentorship program is about. And we're learning some spiritual principles here, right? The principle that when you create an authority in your mind, this is a big thing that we're encouraged to do by society. Oh, so-and-so said this, therefore it's true. But it's better to stand alone, be your own authority. Never allow another authority. Don't be a follower. The real teacher makes you independent and strong. That's what Krishnamurti's big theory is. If anybody's reading Education and the Significance of Life, which Carlos I've recommended, highly recommend. Krishnamurti, Education and the Significance of Life. One of the things he talks about is being independent, psychologically independent, intellectually independent, spiritually independent. And we've got Independence Day coming up. This is a nice thing to contemplate. What is independence beyond the diplomatic independence, right? Beyond the independence of nations. What does the personal independence mean? So we'd like to teach ourselves and the future generations to think independently. And when we approach mathematics like this, we're actually practicing that and sharing that principle, because the way you do anything is the way you do everything. If you eat mindfully, you listen to your girlfriend or boyfriend mindfully. If you eat mindfully, you walk mindfully. If you walk on your phone like this, you probably don't do anything mindfully because you're generating the inertia within yourself. So Robert's like, oh no, Adam was watching me. No, just kidding. I'm sure Robert never walks on his phone. Here in LA, there's lots of people walking around, and I notice people literally walking on their phones, and I can feel them missing the beauty of life, not feeling out with their minds. They're really confined. It's really kind of a problem with phones these days. All right, let's keep going. 15 times 15 is one of my favorites because it's so elegant. Notice how we have 100 in the middle when it shows up here. We have 50 on the top, 50 on the side, and that makes another 100, which is really nice. We have 200s. And then we have 25 in the corner. All right, I want to keep going at a relatively fast pace. 16 times 16, can anybody see it? Ayush. No, you're muted. That's no excuse for not speaking.
Yeah, now I can visualize it.
Yeah, what did you say?
Yeah, I can visualize it. 16 into 16.
Beautiful. So what do you see with this one?
So this is 10 into 6. I mean, like, this is 10 into 10 plus 10 into 6, 10 into 6, and 6 into 6.
Good. So we've got 100, 60, 60, which is 220, plus 36, which is 256. 16 times 16. Now, if you do this for 10 minutes a day, you'll be so fast at this, you'll take it to the next level. You know, it's important to practice Kaizen. In Japanese, there's a word Kaizen. It means continual improvement. When you're constantly pushing your edge to get better and better at what you're doing. And that's where there's a lot of vitality and life energy. So just keep practicing this and you'll take it to the next level. So what we're going to kind of go through the next level, perhaps before you're ready, but we'll do it. So what if I do 21 times 21? Now notice here that we have more sections now. So the reason I've created more sections is so you can see the 400s in there very easily. So 20 times 20, we can see it's 10 and 10 by 10 and 10. Now we see why it's 400. 2 10s and 2 10s. So from this, Carlos, what do you think is 21 times 21? 21 squared.
Well, it would be 20 on one side, 20, and then 4 10s, and then the single one.
Very good. 400s, right? So
400s.
right? Which is what you meant. So 400 plus 20 plus 20 plus 1. 21 squared is 441. How about 22 squared? Okay, somebody challenge yourself. See if you can get it. We're not competing with each other. We're competing with ourselves, of course, always. We got 400. On the top now we have 20 and 20, which is 40. And on the side we have 40. In the corner we have 4. So nobody wants to blurt it out? Blurt out the answer?
Oh,
Jacob, you can blurt out the answer.
uh, I
I like
would say.
how Robert's was that math teacher for 10 years, so he's like, he knows what I mean, blurting it out. Robert, it's your turn to blurt it out. All the kids got their options now.
Is it 444? Or no, 484 would it be?
484. Excellent. Good job.
Yeah, it gets a little trickier with it when you get to the bigger numbers, but I really like this. How you can visualize it.
I was about to
Nice.
say 444 too. I forgot to tack on the extra 80 or 40.
Yeah, I could have drawn these ones on the edges as different, like 4 10s on top. I could have changed the colors like I did for the hundreds, but for the sake of time, I didn't do that. Because as you can see here, I actually had to figure out some logic for how to code this. So I said like floor, all of this logic to change the color of it is a little tricky. So this is all the code for it. It'd be fun to put a little app of this on my website so you could like change the numbers yourself, do it in JavaScript. Okay, so I might do that actually. So let's try 31 times 31. Okay, Robert, let's see if you can yeah, challenge yourself. No, I'm gonna make the picture so you guys can.
So 31 squared, I would assume big middle block would be 300 or 900s.
Okay.
Yep. So that's the main main group there. Then you got a 30, 30, and a 1.
Mm-hmm.
So 961.
Woo! Wonderful. 961. Anybody want to do 41 times 41?
Adam, are you familiar with teaching through algebra tiles? I know they use something like that in school. A lot of like the elementary to middle school kids or teachers might use it, but I never really got to use it in high school. I kind of shied away from it. Have you heard of that method?
I have, and they have manipulatives, which are like little actual physical objects you can put together. But we're like, so this isn't the most novel thing. This is like a Montessori approach, although we're going to try and take it to the next level. When we do cubes, we can do all kinds of things, but this is definitely a starting place for elementary. But really, you called it algebraic. That's interesting.
I guess I was just thinking of those those physical blocks in a lot of.
But is that the official name, algebraic?
I don't think so, honestly. That might be a different type of thing, not the actual.
Well, because it is algebraic. Because what we're really doing is we're generalizing, right? If we generalize this, you'll notice it's always 2 times the 2 orange sections, right? And 2 squares, a big square, a little square, and 2 orange sections. So it becomes algebraic when we generalize the numbers to be x's and y's or whatever letter we like. So, but speaking of being novel, I don't like to compare it because I was coming from a spiritual place when I developed this, and perhaps I got some hints from people here and there. I don't think it was Montessori. It might have been. I don't remember exactly, but the whole idea is we're seeking to see these things directly, and we don't want to limit it to the current methods that are out there, because there's so many ways you can do this. You can do calculus this way. You can do all kinds of things this way, but we should definitely be learning our multiplication this way. All right, so 1600s, right? 41 times 41, 1600s. If I made the hundreds very easy to count, we got 400 by 400, right? So 4 times 400s. Now there's a little memorization when I said 16. Right? Because 4 times 4, why is that 16? Well, you can even count the 10 in here. There's 10 there, 4 and 2, so there's 16 total. So you can really challenge yourself to do this better, right? You may have the answer and say, wait a second, I kind of cheated a little bit, or I didn't really see it. And you can sit with these questions. You can sit with it and be with it, hold it in your mind. You can do them fast, you can do them slow. The whole idea is to augment your state of mind and your mathematical perception. Okay, one of my favorites is 51 times 51. Because it comes out nicely. We've got Carlos, you want to give this one a shot? Do you feel like it?
Sure. So that's going to be.
You know, it's interesting. We talked about in last Thursday about insight from silence. And I like what you just did. You closed your eyes. And there's no rush. If you close your eyes and an hour later you open them and you said, I just went into nirvana, I think you've achieved your goal. Right? Forget about
Right.
the math, right? So if we close our eyes, it's not something we want to rush through. And there's a lot of egotistic competition that's encouraged in school and in society. And it's okay to just like close your eyes and be with it. Maybe sit and experience it. You know, when we feel the psychic pressure from others, it's hard to think clearly. You know, and it's not cool. It's not cool, right? It's nice but so this is an environment where we're really bringing that into the light and saying, okay, I'm gonna close my eyes, you know, take a breath, and begin to see this quantity.
Is it 2,101?
100. Okay, so you got the 100 from the two oranges, right? Because each of those is 50. But how many squares do we have here?
5. Oh,
Five.
5. Wait, 5.
5 times 5. Just kind of revisit that. Okay, 5 times 5. It's 25. So we have 25 hundreds, not 20 hundreds, right?
Mm-hmm.
And then we've got orange and orange. So 25 hundreds. And then everything else you did is correct, right? So you want to say the answer?
So it'd be 2,501.
Close, because it's 2,500.
Oh, sorry. 2,500 or 2,601.
Yeah, there you go. And it's good to go through the process of, okay, I see it. Now, actually, Carlos, let's stay with that. Just because it's done doesn't mean it's done. Hold it in your mind. 2,500, 101. Okay, stay with that. 2,500, 101. You see, you don't have to rush through it. And once you get it, you're actually storing energy in it. There's an interesting thing in shamanism and spirituality. Storing power is one of the ways to talk about it. When you do something and you make this a part of your making sense of reality, you store spiritual power in it. So this is like you've just stored, you've like put a little bit in a special bank account here, spiritual power you can access. If you make this something you really know. I draw power from this. I draw power from 20, from 51 times 51. This helps me order in infinity better. I'm not just saying fancy sounding spiritual words. Like I mean it. This is an important part of my consciousness. I look at, there's not many things, but one of them is this. This is a part of me. And when I do that, I draw power from it. There's a power in orienting powerfully in the universe and structuring your mind in a particular way and having in your tool set these things to focus on. You know, one day you might be feeling a little off for whatever reason. And you're like, okay, 51 squared, 2,500, 101, 2,601. There's order there. Spiritual mathematics. All right, so let's try 52 squared. Jacob, your turn. Assuming I don't want to make anybody uncomfortable, but don't be uncomfortable. You can always say pass, right? If you need to, like, well, I'm getting flustered, I don't want to do it. Pass. Don't do it, right? You need to go inward, you can pass. Or you can just go inward while we're talking about it. $52 times 52.
That's 2704.
Nice.
That's
What about 53 times 53?
let's see. 20. That's 2809.
Yeah, there you go. Okay, so just so you know, Jacob just squared 53 in his head and saw it as self-evident, said it's 2,809. Pretty cool.
That's powerful.
Nice. Yeah. So, and then if you were to do it algebraically, you might say 10x plus 3 squared, right? Let's just, since Jacob was already onto the algebraic part, 10x plus 3 squared, which is basically what this is, where x is 5. Right? So if you were to try not to do it in the traditional way, 10 times 5 plus 3 squared. Okay, we have, now if x is arbitrary, maybe I'm going a little too far right now, perhaps. I'm gonna try it. So, okay, so we have 100x squared, which we can see, right? We had a 5 by 5, right? 5 by 5, so we had 100 times 25. So 100x squared. Actually, let's not do this. I feel like it's maybe too much of a jump. But you can see you will get the +9 over here. We'll do it another time. That's definitely you definitely don't want to jump into having coefficients on the x term and just start with something like x plus y squared. We'll get to that if we have time. Okay, so there's other ones like 101 squared. 101 by 101. So that's actually 10 by 10 hundreds, right? So we actually have 100 hundreds. And you could also maybe count it across, we've got 1,000 on the bottom row, 1,000 on the next row. Okay, so we have 10,000. On the top, we have 100 oranges. On the bottom, we have 100 oranges and one in the corner. So 10,201, 101 squared. So what's 100,000? So it would be the same thing.
10,404.
Yeah, there you go.
Yeah.
Wonderful. Okay, 100 squared.
10,009.
Everyone's fast. That's fun. Now you can think this fast. So 1,000 squared. That means 24 is 6. 2 squared is 6. Let's take a minute while I figure out what to do with the code here. Wow, how to do this? Yep. One 1,024. So 1,000 times 1,000 is 1.
So 10 lakh 48,576.
What word did you use an Indian phrase term? I don't know. 10 what?
Or like 1,000,000, 48,000 and 576.
Good job, Ayush. But tell me this word. It's like it means 10,000. Is that correct? 110,000s. It's like a different kind of number system.
Like 1,000 into 1,000. So it is 10 to the power 6. So which is
But what did you
one
did you say
10 lakh.
lek? 10 lek?
Yeah, yeah.
What does that mean? That's what I'm asking you.
Okay. So it is 1,000 into 1,000 is 10 lakh.
Ah, okay. So 1 lek is 100 times 1,000.
Yes.
Okay, so okay, that's cool. Lek. So you don't even have a term for a million in India, right? They just
Yeah, we don't have a term for million. We say 10 lakh.
okay. So you don't have to be a millionaire, you can be a lekkionaire.
Yes, and after that we do crore.
What is it?
So like
It's
uh
100 million, right?
1,000. Yeah, yeah. So
100.
a billion. So
Oh, it's a billion.
that is
Okay.
crores.
It's a billion is the next number. So
Yes.
in Japanese, they also do that as well. They have like different number systems. So I'm sure other languages as well. Okay, so let's take a look at what I've done here. Good job. So Aish got 1,000 by 1,000 is a million, and then we've got actually 24 thousands on top, 24 thousands on the side, and then 576 in the corner. Now, why is that really useful? Well, 2 to the power of 10 is 1,024. So 2 to the power of 20 is 1,048,576. So you see there's like kind of interesting things you can do. So, because 2 to the power of 10 times 2 to the power of 10 is 2 to the power of 20. If we multiply 2 10 times and we multiply it 10 more times, now we've multiplied it 20 times, and that means 2 to the power of 20. I want to stay on subject, but okay, so what did I do here? So this actually is a little backwards. If you counted out these blue squares, you'd notice there's only 19 of them. So this is really 20 by 20. This may be a little confusing because I was using this as if the blue is 10 by 10. So I hope it's not too confusing. But what we're really saying is that 20 by 20 minus all of this would be 19 times 19. So 400, there's 400 total squares here, minus 19 or 20 on top, including the blue, and another 20 on side, including the blue, but then we took the blue away twice. So you see what I'm saying? If you take 20 off the top and 20 off the side, we turn 20 by 20 into 19 times 19. And you're probably thinking, well, you can't take the blue off twice, right? So we have to put it back. Somebody tell me how I'm being confusing right now so that I can fix that. So yeah, Robert, please.
I guess I don't know. I was following you, and then you're like, then we're obviously thinking about more blues, and I wasn't thinking about more blues.
Okay,
I get
yeah.
like take away the orange, take away the orange. That's drops it down to 19. I was just a little confused where you said the blue thing there.
So this is 20 by 20 right now.
Yes.
If we took this top one off all the way to the blue, we're actually taking
Okay.
we're taking 20 off when we do that because it's 20 wide.
Sure.
And instead of taking 19 off here, which is a little confusing, let's just take 20 off here as well. So I'm allowing myself to use the corner twice. So I'm taking 400, subtracting 20 twice, but then I'm recognizing that I should really add one more blue back. I should add that corner back because I used it twice, which obviously it's not actually there twice. It's only there once. So I add it back. So 19 times 19 is 361. 400 minus 20 plus 1. So 29 times 29, we would have 900. We would subtract 30 off twice and add 1 back. Right? Perhaps it's easier for me to just make the base 10 again. I think of it as like negative, they're like negative boxes. So anybody feel good about 29 times 29? Oh, Jacob, I can't hear you.
841.
Nice, exactly. So he took 30 off the top. He took 30 off the side. So he's 840 now, because there were 900s. And now there's 840. So what's 20? Well, let's do 49 times 49. That's a nice one. Ayush, let's hear it. 49 times 49. So
2401.
did you say 2401 or 5401?
Yes.
24.
Just a minute.
I'm not sure which one it is. We're taking 100 off top, 50 off top, add back 24. So 50 here. What is 8 squared? I'm going to go fast. If it's fast, it's hard. Here. We have 100 by 100 is 1,000. Take off 20 on the top and add back.
94.
9604. Good, good. What is 999 squared? 1,000 times 1,000 is a million. We have a million. We take 1,000 off the top and the side, or 2,000s off the top and 2,000s off the side, right? So million minus 4,000 is 996,000, and then we have to add, and then we have the corner is actually a 2 by 2 adding back. So we actually took 4 off twice, so we have to put 2 back. So 998,004. Cool. All right. So you can also do this in 3 dimensions. So if I said, what is 11 times 11 times 11? You could say, okay, I mean, it's a little harder to see, and I didn't do an animation for this, but we've got the cube of 10 by 10 by 10. To build it out to 11s, we have to add a whole face here, a whole face here, a whole face here, and then 3 edges and a corner. So I think if you're building it out, we would have 100 by 100, 3 faces that are 100, and 3 edges between those faces that are 10. And then 1 in the corner. So just think of a 3-dimensional version of this. We'd have to like bring the layers out, not just around the top and side, but around 3 sides. Not 6, just 3. So what's 11 cubed, Jacob? Throwing you guys right into the ocean, deep ocean here. Throw them in. What?
I'm trying not to cheat right now. I'm
Oh.
trying to not, so
Okay, nice. Can you see 3 faces of 100? Can you see 3 edges of 10? And then 1 corner. Ayush, can you see it? It's a little tricky. So we would have 1,000, 300s, 3 10s, and 1. So 1331 is 11 cubed. Let me challenge myself. 21 cubed, harder. 20 by 20 by 20 happens to be 8 of those thousands, so it's 8,000. Then we've got 400, 20 by 20, 400, 400, 400. So it's 1,200, so it's 9,200. And then 8 in the corner, 9,208. Did I get it right? It's 21 cubed, 9,208. I think so. I'm not using a calculator.
Can you talk through it again? So 21 cubed, you said, okay, obviously 20 by 20 by 20. I was with you there, but then you just you went into your own head and I didn't follow that part. Can you just talk through that again? How you would
sure.
do that one in your head?
So if we had this cube like this, And we're kind of thinking of it like each of those is 1,000. And we're going to build it out another layer like this. Each of these is 400. They're
So
only
every edge, huh?
every edge. Yeah, not every
It's
edge.
okay, an additional thing. That's what I was having a hard time visualizing, is whether that would actually come into play. See, I get the
Yeah.
20 by 20 by 20, and then that extra edge on every single side, and then one on each corner. So all
So it's actually
8
not on,
corners.
it's not on every single side. It's on just 3 sides in this case.
Okay, that's what I was confused about.
And
Thanks for
then,
clearing that up.
yeah, sure. And then we have these 3 pillars. Right, so we have 3 faces and 3 pillars. And remember, each of these faces is only 1 wide. So these are 400 each. And these are, did I make a mistake? I did make a mistake. These are 20 each. I don't think I included the 20s. So we've got 8,000 behind there. We've got 1,200, which is 9,200 from the 400s and the 8,000. So we've got 8,000, 1,200, which is 9,200. And then we're going to add 320s, which is 60 and 1. So 9261, 9261. So if we were to do 31 cubed, we would get 27 thousands. We would get, each of these would become 900. So we 27 thousands, 2,700, which would be 29,700. Each of these would be 30, so we'd be at 90, 29,731. I think I got it right. 29,731. You guys can check me with a calculator, but that would be 31 cubed. So it's 27 thousands, 27 hundreds, 330s, and 1. Good. Now you don't have to only do it all. So the way I'm doing it here is just building the cube. And then if we do 3 sides, we're just doing 3 sides, but we're leaving the other sides out, right? 12 times 12 times 12 works really nicely because you can actually do 1 on each side. So if I do 1 there and 1 back here, if I do 1 here and 1 back here, if I do 1 underneath and 1 on top, we've actually built it out 1 on 1 on each side. So now 10 became 12 by 12 by 12. And it's one of the most beautiful cubes because 12 cubed is the same thing as 1,000, 6 faces of 100, 12 edges of 10, and 8 in the corner. So that's 1,728, which is 12 cubed. That's the number of inches in a cubic inches in a cubic foot. There's just some ways to see this. Now, notice I was being creative. I said, well, hey, let's not put them 2 on each side. Let's not put 2 on 3 sides. Let's put 1 on each side to build it out to 12. Right? So you can be very creative the way you do this. Did that make any sense? Did that make a little sense? I'm trying to just use the last 5 minutes to go a little further so you can take it as far as you want. I don't expect anybody to follow that. If you did, perhaps you've already cultivated this, or you're just really really primed for it. So you can also do 4th dimensional versions. If I were to say what's 17 times 17 in base 16, now you can say, okay, well, it's 16 by 16, which is like 100 in base 16. Means instead of base 10, we're thinking of 16 by 16 as 100 because it's one set of sets. And then we've got 2 16s and 1. So 17 squared in base 16 called hex hexadecimal actually is a better name for it, is the same thing as 1 to 1, 121, but really it's 1 16 16, 2 16s, and 1. And if you were to actually do hex in computer science or something, you would find that's actually the answer. You can also go backwards. 15 times 15 is like 16 by 16 minus 2 16s plus 1, which would be 14 16s and 1. And in hexadecimal, 14 is represented by the letter E. So it would actually be E1. So F squared, where F is 15, is equal to E1. So I'm just showing you just a couple of things that get a little bit more crazy. But you can take this into different bases like that. So what's F squared? E1. You can see it exactly in the same way. So Carlos, what do you think? Please don't be discouraged by if I'm taking it too fast, just for the end part.
Yeah, I kind of was having a hard time following along at the end. I think like just grasping like in the millions, um, which I feel like I don't know. I mean, I don't have too much experience with numbers. Never been very good at math. But I thought it was really cool that I could visualize those first few exercises. I've never had that ability to even
Nice.
square anything like that in my head. Like I just realized. I think you said at one point when we were squaring 25. I didn't even realize I was doing that until you said like, oh yeah, we're squaring these numbers.
Yeah.
Like we're squaring them in our head. I was like, oh, like it just kind of clicked. But
Love it.
yeah, this is amazing.
Love it. Yeah.
I have a question of
Sure.
like, what is there like things that can be done to practice or like get better and build that
Yeah.
sort of capacity for this? Or
Absolutely. So here's a little exercise sequence for you guys, and then later on it'll be easier for you to do the other stuff that I've added in the last 5 minutes. So just ignore that for now unless you feel it's relevant to you. Perhaps, so I've suggested 15 minutes a day of math. You sit down, you close your eyes, and do math for 15 minutes with your eyes closed. You can do it with a piece of paper, but sometimes it's nicer to do it with your eyes closed. You could do 11 times 11, 21 times 21, 31 times 31, all the way up to 101 times 101. That's a nice little sequence. When it gets too easy, you can say, okay, well, let's maybe do 22 times 22, 32 times 32, all the way up to 102. You can also do 19 squared, 29 squared, 39 squared. You can try those ones. So basically go through and explore using this in just perfect squares. That's a good place to start. You could also start doing things like what's 21 times 22? Rectangles, right? So 21 times 22, we would have 2 on top and 1 on the side and 2 in the corner now, right? So it changed a little bit. So just practice those, and you know, maybe if you don't want to close, you could do it with your eyes closed. Maybe in the beginning, just grab a calculator and just see if you can get them. You know, sit down for 15 minutes a day. If you do 15 minutes of meditation a day and 15 minutes of this a day, I think it should really start to change how you feel in your own energy, in your own body, in your own mind. So that's what I recommend. Yeah. Yeah. All right. Let's do a little meditation and close out for today. And after doing math, when we meditate, we can feel the structures. In fact, if you feel your third eye, or your heart and your third eye, you can feel the order. Being grateful. Thank you, everybody. So you may have noticed there's no females here. Invite your girlfriends. Let's make this not a boys' club. Bring your wives, bring your female friends or your girlfriends so that we can have a little more balance in here. Yeah. Want to bring the yin feminine energy into mathematics, make it a little bit more balanced, not only just with the people, but in the way it's done, because math is so masculine the way it's done in society, and that's not innate to mathematics. Somewhat, but I wouldn't say it's entirely innate to mathematics at all. And what else can I tell you guys? Tomorrow we're doing my favorite topic, Bhakti, the yoga of love. We'll do that in our meditation tomorrow, same time. I'll be talking about what Bhakti is, how you practice it. Bhakti changed my life massively. It really, really made me a lot happier in a lot of ways. So I'll be talking about that, and we'll be doing a heart-centered meditation tomorrow. So I hope you guys make it. And then on Wednesday, what do I have on the schedule? We have a mathematical coding on Wednesday. I think can't remember what it is. Although we might do something else because I think it was a little too advanced last week, and I'd like to make sure everybody gets up to speed. So last week we just went over some basics. And then Thursday we have the mentorship program. So hope to see you guys there. Namaste. Happy July. Best month. One of the best months. One of my favorite months. All right. I'll see you next time. Thank you.
Thank you.
Yeah, nice to speak, Carlos.
Oh, Adam.
I love Carlos's background, by the way. What is that? It's a 60-sided shape, I believe, right? Is that a Bucky?
Yeah, it's a geodesic dome.
Nice.
I have like a PVC version, but
Nice.
again, I want to learn more about kind of like the mathematical structure behind it. I know there's a lot that goes into it, and
I love that. Yeah. Well, maybe we should do a class.
yeah, I have one in my backyard, but
Oh,
yeah,
cool. Yeah, those are great. Those are great. I love that you have one in your backyard. That's awesome. What did somebody else say something? I think it was it Robert or
Oh,
Jacob? Robert. Jacob?
Adam, you should check my comment in the.
You're very close. It's actually 1729. So 1729 is 12 cubed plus 1 cubed, and it's also 10 cubed plus 9 cubed. And yeah, Ramanujan said that. But I hope I'm not making you feel bad for correcting you. Okay, good. But you see, but you knew about that. I love that you brought that up. And one of the ways you can see 12 cubed plus 1 cubed is with this technique, 1728, 1729. And if you haven't watched The Man Who Knew Infinity, highly recommend that film. He actually talks about it in that film. So
That's a very good movie.
yeah, it's really great. So I like that. Yeah, 11 cubed is good too. I like 11. Ramanujan should talk about that one. All right, guys. I'll see you later. Did we do pretty good with timing here? Okay, we only went kind of like 5 minutes over. Good. All right. I mean, we started 5 minutes late, went 5 minutes over. Okay. I'll see you guys next time. Thank you.
Yeah.